This is section 13.2 that deals with saturated, unsaturated, and supersaturated solutions. But pretty much we can summarize that into exploring the solubility concept, right? Up to this point, you should be able to tell whether something is soluble or not if we apply this to water. But here in this section, we want to explore, well, when we say that something is soluble, well, how much soluble that is, or if you say that something is insoluble, well, kind of quantifying the solubility of these solutes, particularly in water. In this section, we are kind of limiting our discussion to solid in liquid solutions and gas in liquid solutions. Okay? And when it comes to solubility, there are two things that we might think of when we come to solubility. So, to what extent something is soluble and to what extent something is insoluble. And two things that I want you to keep in mind when it comes to solubility. Nothing is infinitely soluble, particularly if we are discussing the solid-liquid solutions, and nothing is completely insoluble. Okay, so you have a wide range of situations here. In section 13.2, we are going to take care of this concept, the concept that nothing is infinitely soluble. Later in the semester, we will take care of that nothing is completely insoluble, and we will discuss that in more detail later. So we are taking care of gaseous and solid solids, particularly in a liquid. Okay, and there is a dependence. What things that control how much you can dissolve at any given time? Well, temperature has a big role here, and normally, as you increase temperature for a solid, the solubility will increase. You will be able to add more solid to that solution if you increase the temperature. But the opposite is true for a gas. But we're going to take care of the gas later. Okay? So whenever you start adding the solute and whenever you reach the maximum concentration that you can have in that solution, then you say that the solution is saturated. And what it means by saturated is that if you try to add more, then it will not dissolve, and then it will remain as a solid below the solution, if you will. I mean, it will, assuming that the solid has a higher density than the liquid, which normally is, the solid will just remain at the bottom of the solution. It will not continue dissolving. Okay? That is your saturated solution. Now, if you add some of the solid and it completely dissolves, then right before you get to that saturation point, you will have an unsaturated solution. Meaning, and with an unsaturated solution, you can continue adding the solid and it will continue to dissolve. Once you reach the maximum, then you obtain the saturated solution, and it will not be possible to dissolve any more solute. So we express this behavior with a graph or a solubility curve. We call this as solubility curve. And normally what we see here is the amount of solid that you can dissolve in a given amount of water versus temperature. The temperature will increase left to right, and the solubility will increase as you go up in the graph. Now, what I want you to keep in mind here, this is not the concentration that you are used to handle. Here we are determining how much you can add for a given amount of water. We are not looking at the amount of solution, we are looking at the amount of water that is present in that solution. So if you look at here, then it's expressed in per 100 grams of water, not 100 grams of solution, 100 grams of water. Okay? So, and normally what you can see in this graph is that as you increase the temperature, the solubility will increase. You will be able to add more of the solid into that solution. Based on this graph, there is one kind of the opposite behavior here, which happens for sodium sulfate. This is not very common. Okay, so for the most part, most of the solids, the solubility will increase with temperature. And we are able to extract information out of this graph. How? For example, we are looking at lead nitrate here, and lead nitrate, well, we have to look at what the curve for lead nitrate is, and lead nitrate is here. So we are looking at the yellow curve here. Now, how much lead nitrate you have to add to 100 grams of water? This is very important. 100 grams of water at 50 degrees. Okay, you want to obtain a saturated solution. So how much you have to add of lead nitrate to saturate a solution containing 100 grams of water? Where do we start? Well, we start at 50 degrees, right? And 50 degrees are right here. So we go up on that 50 degrees until we connect with the curve. And if we extend the curve to the other axis, well, this should be approximately 85 grams. Okay, so you can add 85 grams of lead nitrate in 100 grams of water at 50 degrees, and that will give you a saturated solution. Okay, so the answer here is C. Okay, you can do that with every single substance present in this graph. Okay, so in what other ways can you handle this information? So, well, before we get there, when you have saturated solutions, remember, if you have a saturated solution and you want to add more solid to that solution, more solute, then you have to increase the temperature. That's the way that you can add more. But what happens if, for whatever reason, once you reach your saturation and you are at a certain temperature, what happens if you decrease the temperature? Right? If you lower that temperature, then one of two things will happen. Okay? If you lower the temperature and the amount of solid that you have dissolved there will be past the maximum amount that you could possibly dissolve. So normally that means that the solid should start coming out of the solution because you have more than you can dissolve. So it's natural that it will come out of the solution. It will precipitate out of the solution. But sometimes, depending on how you do this process, how you do that cooling, sometimes you reach an unstable situation in which all of the solid remain in solution, and in that case you will have a supersaturated solution. So simply put, a supersaturated solution is such that have more solid that you should based on the solubility. Okay, it's past the point of saturation. And yeah, on the normal conditions, it might happen, but these solutions are very unstable. So any perturbation that you do in the solution will cause the solid to come out of the solution. Okay, and this is part of these saturated solutions and supersaturated solutions is part of the process of recrystallization that most of the time is used to purify compounds. Okay. And nothing to worry too much about recrystallization right now, but it's just, this playing with these solubilities and temperature is what allows you for recrystallization and purification of certain substances. So in this case now, we have that, we don't have the curve, the solubility curves, the figure, but we have the data on solubility. And in this case, per 100 grams of water, sodium acetate, it doesn't really matter which one is it as long as you have the data. You can dissolve 119 grams at 0 Celsius and you can dissolve 170 at 100 Celsius. Okay, So 119, let's put it this, 119 grams at 0 and 170 grams at 100 Celsius. Okay, so the first question is, if we have 170 grams of sodium acetate and we put it in 100 grams of water at 0, how much will it dissolve? Well, if you have 170 grams of sodium acetate and the solubility is 119 grams at 0, then 119 grams of sodium acetate will dissolve, and well, the difference is 51 grams remain undissolved. Okay, now, is the resulting system homogeneous or heterogeneous? Well, if you have some of the solid that is undissolved, then you will have a solution and a solid. So you can distinguish between two components on that mixture. It's not a solution, you have a solution on top of a solid. This is a heterogeneous system. Okay? Now, the solution, is it saturated, unsaturated, or supersaturated? Well, if you are at 0 Celsius and you dissolved 119 grams, then you have a saturated solution. Okay? Now, if you haven't separated anything, you still have your container, you have the saturated solution on top of the solid, the 51 grams that are still undissolved. What happens if you raise the temperature to 100 Celsius? Well, you started with 170 grams, 119 that are dissolved, and 51 grams that are still out of the solution. If you increase the temperature to 100, you are increasing the solubility to 170. If that's what you had at the beginning, then you end up with a homogeneous system, because the solid that was initially undissolved now at a higher temperature will dissolve, and then you will obtain, just for the fun of it, now you are saturated at 100 degrees. Okay, which I pretty much believe, yes. The next question, at 100 degrees, is it saturated, unsaturated, or supersaturated? We already answered that is a saturated. Now, if we cool the system back to 0 Celsius, and at 0 Celsius you can only dissolve 119 grams, okay? However, you cool it in such a way that there are no crystals. Nothing appears. Technically you have, if nothing appears, you are having a homogeneous system because you only have the solution. Now, if nothing appears, you have, in this situation, once you are back to 0 Celsius degrees, you have 170 grams of sodium acetate in 100 grams of water at 0 Celsius, which is obviously past the point of saturation. Therefore, at 0 Celsius, if you have this situation, that is a super saturated solution. Okay? Now, if you had the graph and you want to know, well, in this graph, how do I recognize when is a saturated, supersaturated, or unsaturated solution? Well, points on the curve they are saturated. They represent saturated solutions at the given temperature. Okay? Above the curve, that is supersaturated. Why is it supersaturated? Well, if you let's take a look at any of these curves. So let's assume that we are going with the potassium nitrate. Okay, let's say we are at 10 degrees. Okay, the solubility here tells you that at 10 degrees you should dissolve about maybe 45 grams of lead nitrate. Okay, but if you continue going up and you go all the way here, 60 grams. If you have 60 grams of lead nitrate dissolving 100 grams of water at 10 degrees, then you have more than what the solubility tells you, and that is supersaturated. Okay? Of course, if above the curve is supersaturated, then below the curve is the unsaturated region. Okay, so once again, points on the curve are saturated. If you are above the curve, is supersaturated, and if you are below the curve, then is the unsaturated region. Okay, so now let's go back to our problem here. Now we are dissolving 30 grams of potassium chloride in 200 grams of water at 50 degrees. The question is, will you obtain a saturated, unsaturated, or supersaturated solution? So we locate our temperature. We are looking for 50 degrees, right? So we have 50 degrees. Then we go up. We are working with potassium chloride, which is right here. So it's the green curve. And then we locate our 30 gram mark, which is there, right? So you're going to tell me, well, that looks like it's a supersaturated solution because you are above the curve. However, remember that these are grams per 100 grams of water, and you are dissolving 30 grams of water in 200 grams of water. Okay, so let's write that down. So we have 30 grams of potassium chloride in 200 grams of water. That is equivalent to say that you are dissolving 50 grams of potassium chloride in 100 grams of water. So you have to be careful with the amount of water that you are playing with, because now it's not the 30 that you are looking at here, you are looking at 15. And if we look at 15 here, which is right about there, we are just below the curve. Okay? So that means that 15 grams of potassium chloride in 100 grams of water at 50 degrees, that's actually a unsaturated solution. So pay attention to what amount of water you are working with. It could be more than 100, it could be less. Just multiply by the proper factor to put that point over on the chart. Okay? Convert that amount of water to 100. Whether you have to multiply, whether you have to divide, and whatever you do to the amount of water, you do to the amount of the solute. In this case, to get to 100 grams of water, we divide it by 2. Okay, but it's whatever you have to do to the amount of water to make it 100, and you do the same to the amount of solute. Now, when it comes to gases, gases behave a little different than solids, because normally for a solid, not for every solid, but for most solids, if you increase the temperature, you increase the solubility. But with gases, it's the opposite. If you increase the temperature, the solubility of gases will decrease. And why is that? Because remember, if you remember, gases is all about kinetic energy. The more kinetic energy, the easier it is for the gas to go to, or for the liquid, for that matter, to go into the gas phase. Now, here you are looking at gas molecules that are somehow in the liquid phase. If you increase the energy of those gas molecules, then it will be easier for them to go into the gas phase. So that's why increasing the temperature of the solution will decrease the solubility of the gas, because the gas will prefer to be in the gas phase and not in the liquid phase. Okay, how do we determine those concentrations or those solubilities of the gas? Well, we have the Henry's law, which pretty much looks like this. The molarity of the gas is equal to a constant. Let's be specific here. This is the molarity of the gas. It's equal to Henry's constant, which depends on the gas, of course. And here the pressure, this is partial pressure of the gas. Okay, so if you increase the partial pressure of the gas, you will increase the concentration of the gas. Okay, of course these constants are also temperature dependent. We are not going to worry about temperatures here. We can assume that we are always working at the same temperature, so we only worry about the pressures, okay, and the concentration of that gas. So how do we use this equation? So let's assume that we have oxygen, and that at 25 degrees, so that we can use the Henry's law constant, what is the solubility of oxygen if the pressure of oxygen, of course, is 2.3 atmosphere? So here the molarity of oxygen is going to be equal to Henry's law constant for oxygen times the pressure of oxygen, and this is simply for oxygen is 1.3 10 to the negative 3. 1.3 10 to the negative 3. Pay attention to the units, is units of molarity divided by atmospheres times the pressure of oxygen, which is 2.3 atmospheres. Atmospheres cancel with atmospheres, and then we obtain that the concentration of oxygen is 2.99 10 to the negative 3 molar. And let's see, because of significant figures, this is probably more like 3.0 10 to the negative 3 because of significant figures. Okay, so it's an equation that is rather easy to use. Probably one of the most common situations in which you are going to use it is when you actually don't have the constant. So what happens if you don't have the Henry's law constant? So if we remember correctly, this is your Henry's law equation. Molarity equals the constant times the pressure. If we solve for the constant, then we have that the constant is equal to the molarity divided by the pressure. Now this is useful because now if you have a gas and you have different conditions of pressure and you want to know what the concentration is, then we can write this is condition 1 and this is condition 2. It's the same gas, okay? This is really important. We are working with the same gas. So because of this relationship right here, okay, we can say, because it's a constant, we can say that M1 divided by pressure 1 is equal to M2 divided by pressure 2. And it all depends. This is similar to some other equations that you may have used in the past. You have two conditions. You want to know, you have 4 variables here. You need 3 to solve for the 4th one. So how do we use this one? Again, at 25 degrees. And it doesn't really matter the temperature now, because you're going to cancel the constants anyway. So you have a pressure of 2.54 atmospheres, and the concentration of CO2 at that pressure is 8.6 10 to the negative 3. So I'm going to call that P1 is equal to 0.254, and I'm going to say that M1 is equal to 8.6 10 to the negative 3. Now we want to know what is the concentration of CO2 if the pressure is increased to 0.419. That's pressure 2, 0.419, and I'm forgetting here that these are atmospheres. So basically the question is, what's the value of M2? Okay, so M1 over P1 equals M2 over P2. This means that M2 is going to be equal to M1 P2 divided by P1. So that concentration is going to be equal to the initial concentration, or 8.6 10 to the negative 3, times this pressure 2, 0.4119 atmospheres, and I'm forgetting that this is molar, divided by 0.254 atmospheres. Atmospheres cancel with atmospheres, and then we end up with 1.42 10 to the negative 2, and well, everything is, well, the smallest number of significant figures is 2, so we should report this as 1.4 10 to the negative 2. So the answer here is C. So probably this is one of the most common situations that you are going to have. You have two conditions, and then you want to know what happens on the second condition, okay? Whether you are increasing the pressure, or at what pressure you have to change so that you change the concentration, okay? So in review, we've been discussing about saturated, unsaturated, and supersaturated solutions. A saturated solution is going to be that one that have the maximum amount of solute that you can possibly have in a given amount of water, okay? If you add more and it's completely dissolved, you have a supersaturated solution. If you are below that maximum amount, you have an unsaturated solution. When it comes to gases, the behavior of the gases is different from the solids. The solids will increase the solubility as you increase the temperature most of the time. For gases, it's the opposite. The solubility will decrease if you increase the temperature. You relate the concentration of that gas with the Henry's law, which depends on the partial pressure of that particular gas. So if you increase the partial pressure of the gas, you increase the solubility of that particular gas. Okay? And we kind of reserve the terms saturated, unsaturated, and supersaturated to solids in liquids. It doesn't really make so much sense when you have a gas in a liquid, or for liquids for that matter, something that we haven't discussed here. Liquids in liquids sometimes are what we call miscible or completely miscible, meaning that there are no limits to the proportion in which you can dissolve a liquid in a liquid. That's why we are kind of limiting our analysis here in this section to solids in liquids and gases in liquids for that matter. Okay, so this is it for now. Next up would be talking about concentration units, which I think is going to be fun.